start the next talk, and it's by Vanessa Stiles from the University of Sussex, and it's about multi-material structural topology optimization.
Okay, so thank you very much. I'd like to thank the organisers for inviting me to this very interesting meeting. And so my co-workers on this project are Louisa Blank, Hassan Farish Bafshaker and Harold Garker. And for the outline, so what I'd like to do is I'd like to give you the basic ideas of structural topology optimization, and then the approach that we're going to look at is the multi-material phase field approach. So I'll define that, and I shall also then tell you about the structural optimization problem associated with this multi-material approach. And then I'll briefly derive the first order optimality conditions for this problem, and then finally I want to finish with some numerical simulations. So this is the idea. Our goal, what we want to do, is we're going to have a design domain. So in this particular picture here, the design domain will be the rectangle, and we'll call that omega. And what we want to do is we want to distribute a limited amount of material in this design domain, such that an objective function of j is minimized. So what we need to do is we need to find omega m. So here capital M stands for material. We want to find this region of material and displacement u, such that we've got linear elastic material here, and we're going to have volume forces acting, surface forces acting on the boundary, and it may be necessary, or we may wish to prescribe a fixed region of material somewhere in the design domain, and also a fixed region of void. And I'll mention here we've got different boundary conditions. So here we've got gamma capital D. So this is our homogeneous Dirichlet boundary conditions, where we're going to fix part of the domain, and then on where our surface forces are given, we've got these non-homogeneous gamma G, and then we've got a gamma 0, which is homogeneous. So non-homogeneous Neumann is gamma G, and then homogeneous Neumann boundary conditions relate to a hold on gamma 0. So mathematically, what do we want to do? So we want to minimize this objective functional j over all omega m in this admissible set u add, such that, so we need omega m, so our material has to lie in our design domain omega, and we have a fixed amount of material from the beginning. So we have the Lebesgue measure of omega m is going to be some given value capital V, and as I mentioned, we may wish to prescribe these regions. So we're going to have an S0 which will be contained in omega m, so this is a fixed region of material, and then we're going to have an S1 which will be a fixed region, or we might prescribe these, a fixed region of void, such that the intersection of omega m and S1 will be the empty set. And choice of possible objective functionals that people consider. So there's the mean compliance, we'll call that J1, and so this is just the work done by our load. So remember, F was the volume forces acting on omega m, and G was the boundary forces. And in addition, so a second possible objective function is our J2. So J2, what we're thinking of in this context is we want to, we've got a target displacement u omega that we want our displacement u to be as close as possible to. So we just have the, we want to minimize the L2 error between these, with C of x is just some given weighting factor. So those are the two objective functionals we're going to consider. You could consider more general ones, but these are the two that I'll talk about. So J1, when we see J1, so say that's the mean compliance, and then we have this J2, which will be error compared to our target displacement. So the optimization problem that we're looking at, we want to minimize this objective function, so we've got some alpha and beta. So we have alpha J1 plus beta J2, subject to our standard linear elasticity equation. So here, as I said, F was the volume force, G is our boundary force, and we've got the displacement equal to 0 on our Dirichlet boundary, Dirichlet part of the boundary, gamma D. So Cm is just standard elasticity tensor, and this E of u is the strain tensor. The trouble here is the problem isn't well posed, and a possible path to well posedness is you just add to your objective functional here a regularization, so you have your perimeter functional, and so therefore the objective functional that's usually considered will take the form, so we'll have here alpha j1, beta j2, and then we've got this regularization at the perimeter. And so classical methods for solving such a problem done by the following authors. So what they do is they compute boundary variations and shape derivatives to arrive at the first order optimality conditions for this problem. So that was single material structure optimization. So we just had one type of material and we wanted to distribute that in our design domain. What we want to consider here is multi-material optimization. So here we've got this heterogeneous structure. So what we want to do now is distribute two or more materials in our given design domain. So everything holds as before. We'll have some fixed region. We may have some fixed region of material, some fixed void. We've got our boundary forces, and we've got our volume forces, and some Dirichlet part of the boundary which is fixed. But now instead of just having an omega m, we've got, as I say, two or more types of material that we want to distribute into this domain. So here we're thinking of the case of three types of material. So we want to find omega 1m, omega 2m, and omega 3m. And to do this, we consider a phase field approach. And what we do in our phase field approach, so we saw before in the classical methods, there was this regularization of the perimeter functional. So what we do is, as similar to Klaus mentioned in his talk earlier, so we approximate this regularization by the Ginzburg-Landau functional. And one of the advantages of this phase field approach is that it naturally allows for topological changes. So it's very easy to have nucleation and elimination of holes. And also, it's straightforward to construct a multi-phase model. So phase field models have been used for quite some time. So the first to solve such problems, so for single phase, single material optimization. So in particular introduced by Bourdin and Chambol in 2003, and subsequently have been used by the following authors. And in particular, so I'd like to point out that Wang and Zhu looked at multi-material phase field approach, whereas the others were just standard single material. Bensler, Rumpf, and Wirth looked at non-linear elasticity as opposed to the linear elasticity that we're looking at. But in general, the work consisted of just formally deriving the first order optimality conditions, but we want to have a rigorous derivation of them. So, as I mentioned, classically, in general, classical methods use boundary variations, compute the shape derivative to arrive at the classical first order conditions with the regularization of the perimeter functional. So what we do in our phase field approach is, as I said, we approximate the perimeter functional by our Ginzburg-Landau functional, and then we rigorously derive first order necessary optimality system, and also, this is what I'm going to talk about in this talk, together with some numerical results. But we also do via formally matched asymptotic expansions, we recover the first order conditions for the sharp interface model. So phase field approach, so as I said, this is similar to the talk that Klaus gave. So what we're going to do is we've got this vector valued function phase field variable phi. So we're going to have phi going from 1 to n, and this will correspond to n minus 1 materials, because so the phi I for I equals 1 to n minus 1 denotes our different materials, and then the void will be denoted by phi capital N. And we have this epsilon parameter which relates to the interface between these different materials and between the materials and the void. We have a Gibbs simplex, so because we've got this phase fraction of each material, we want our Vi to be greater than or equal to 0, and we want the sum to be equal to 1. So this is our Gibbs simplex. So in general, we want our phase field variable to lie in this set G, such that our function is H1 and lies in the Gibbs simplex. And in addition, as I mentioned, we're going to prescribe the spatial amount of each phase. So each material from the beginning, we explicitly prescribe how much of material 1, 2, 3 is going to be present in the domain, and then it's left to distribute itself. So here's a schematic of the Gibbs simplex, and this is an idea. So if we just take, for example, n equals 3, so we'll have 3 different bulk phases with an interfacial thin with width order epsilon, thin interfacial region between them. So think of this U as being a phi. It's a typo, unfortunately. So for example, we have this bulk region, so you have phi 1 is equal to 0, phi 2, so phi 1 is equal to 1, phi 2 and phi 3 will both be 0. In phase 2, then you'll have phi 1 is 0, and phi 2 will be 1, phi 3 will be 0, and in this region between them, you'll have contributions for phi 1 and phi 2 will both be non-zero, but phi 3 will be 0 and similar. So that's our phase field approach. So the mechanical properties of this system, so as I mentioned before, linear elastic material, you've got a fourth order elasticity tensors Ci, so for each one of our phases, so for the capital N minus 1 materials in the bulk regions, they'll have elasticity tensors given by Ci, and then for the void, so what we do for the void is we model that with a very small elasticity tensor, so C capital N will be, for example, epsilon squared, so epsilon, as we know, is the width of the interface, so small parameters, so we take it to be epsilon squared C tilde N, where the order of C tilde N is equivalent to our Ci's from the material elasticity tensors. So that's what we have in the bulk regions, and in the interfacial region between these bulk regions, then we just have a linear combination. We define the elasticity tensors to be a linear combination of these Ci phi I. So what do? We use Ginzburg-Landau function, as I say, for our regularization and approximation of the perimeter functional. So this was introduced by Elliott and Luckhaus in 91, and we take here this capital phi, so phi is going to be phi 0, so phi 0 we have here, half 1 minus phi dotted with phi, and then we have the indicator function of the Gibbs simplex, ig of phi, so this will be 0 if phi is in the Gibbs simplex, and it will be infinity otherwise. And so now we introduce an E hat, so it's the same thing, apart from we notice here that we're just taking phi 0 and not phi, so we're leaving off the indicator function in our energy. So when we see an E hat, it's, as I said, it's just phi 0, it doesn't have this second term. But we note that if our variable phi is in the Gibbs simplex G, then we do have that E hat is equal to E. And in our phase field model, the two objective functions that we consider, so J1 we have for our mean compliance. What we want is the force to act on the material regions, not where the void is, and we recall that the void is associated with the order parameter when, so phi capital N, and because we have the sum of all the phi i's equals 1, so here this 1 minus phi n will represent the, as I say, this will act on the material regions, not the void region. And we have a similar thing for our compliant mechanism, where we're trying to get as close as possible to our target U omega. So again, we've got our weighting function, and this is multiplied by a 1 minus phi n. So again, we want this to hold where we have material and not where we have void. And so here, our objective functional alpha J1, beta J2, and then this regularization E hat. And so in our objective function, as we see, we're not taking into account this indicator function. So when we look at the problem, so this we can see the similarities between this and an optimal control problem. So here our control will be phi, our state will be U, and so we're minimizing alpha J1, beta J2, gamma E hat. And as I said, because we have this E hat, then we have to prescribe. So we've got this has to be over. We need this to satisfy our linear elasticity equations, and also we need our phi to live in the Gibbs simplex plus the spatial amounts of each material given this GM. and our UC we see here are our sets. So where we prescribe, we have phi n equals 0, so this will be in a set S0. So this was our prescribing material in the domain, and then in our design domain, and we also might have a region where we want to prescribe void, so therefore we'll have that phi n is equal to 1 in S1. So this is our set UC. So that's those are conditions that we want to minimize this problem over. And I should point out, so this is the weak formulation of our linear elasticity. We have that EUEV over C is just the integral, this tensor, and we have our right-hand side is our mean compliance. So we proved that, so as similar to Klaus mentioned earlier, so we have this control to state operator S of phi is equal to u. We proved that this is Frechet differentiable, and indeed that its directional derivative at phi in the direction of h is given by this u star, where u star denotes the unique solution of this problem here, and we get this simply by differentiating the implicit state equation. So before here we had an E of u, so we've replaced that by S of phi, and differentiating this we arrive at our u star, the problem that u star solves. And we can write our function in terms of just our variable phi, so we have the following reduced cost function lowercase j of phi, so we've just replaced all our u's by S of phi, and we can show that this is Frechet differentiable. And the first order necessary optimality conditions, so if we let phi be a minimizer of our problem p epsilon, we get u equal S of phi, then the associated problem can be reformulated in terms of this reduced cost functional, and we get that the following variational inequality is fulfilled, and we can actually work out what the terms of this are relating to our elasticity equation and our objective functionals. So I won't go through this in great detail, but we recall that this is our objective functional. We introduced, similar to Klaus mentioned earlier, so we introduce an adjoint equation, so we've got this adjoint variable p which solves the following equation, and we can look at the derivatives in the direction of phi tilde minus phi, and what we end up with is that this expression here is equivalent to the following gradient inequality that holds for phi, u, and our adjoint variable p. So we have the following optimality system. We've got our state equation, an adjoint equation, and the gradient inequality. And what we want to do, oh, and I should also mention that if beta equals 0, so beta is the term in front of, if we've got our target displacement, we want to minimize the L2 error, that was in front of the beta term. So if we don't consider that term in our objective functional, then what happens if we look, so this beta term disappears, and we just have that EP EQ is equal to this, which is exactly the same as this, apart from it's multiplied by an alpha. So what we actually see is that we have that our adjoint variable p is just alpha times u, so there actually is no adjoint equation if we just consider the mean compliance in our energy, in our objective functional. So numerically, what do we do? So for simplicity, set omega, our design domain omega, to be a polygonal domain. We have a regular triangulation, and we have piecewise affine SH is a set of all phi which are piecewise affine on each triangle, and corresponding to our elasticity variable, so we introduce an SDH such that V is in SHD, so D stands for the dimension of the problem, and we wish V to be equal to 0 on the Dirichlet parts of the boundary where we fix the domain. So we just take a standard finite element approximation of the state equation and the adjoint equation, and then again, similar to what Klaus discussed, we use a gradient descent method to approximate the gradient inequality. So steady state solution of this problem will be a solution of our gradient inequality, and we approximate this using a semi-implicit finite element discretization. So to solve the resulting variational inequality, we use the prime or dual active set method. So this is introduced by Hintemüller Ito and Kunish. And we use the finite element to do the computational results. We use the finite element toolbox Alberta, and we use the visualization software ParaView. So this is just going to end with some numerical simulations. So mean compliance, so the first two are going to be taking beta equals to 0 and just considering the mean compliance in our objective functional. So we've got these two structures, a Mitchell type structure and a cantilever beam. So what we're going to do, so let's take the cantilever beam. So we fix the left-hand boundary. So this is the displacement is going to be equal to 0 down here. This can't move, and we pull in the bottom right-hand corner. And for the Mitchell type structure, we fix the two bottom corners of the domain, and we pull in the middle. So we don't have, I should point out, in all these numerical simulations, we don't actually use any body forces F, so F is equal to 0. We just have these boundary forces G. And then for the compliant mechanism, where we want to minimize the error to a given target displacement, so here we take U omega, our target displacement, to be equal to 0 everywhere in the domain. And in these particular, in the mean compliance computations, our sets S0 and S1, where we prescribe fixed material and void, we don't prescribe anything in either of those, but we do prescribe for our the computations worked without prescribing any regions of fixed material or void. But when we looked at the L2 the compliant mechanisms, to actually get some sensible computations, we saw that we actually needed to fix regions in the domain where we set material. So this is our set S0. So we've in all these red parts of the domain, i.e. where we fix the boundary and also where we impose our boundary forces, we actually prescribe there to be material in these places. So in the Mitchell type structure, what are we doing? So this is just in 2 dimensions. This will just be a single material, so there'll just be material or void. It's not multi-material. We set beta to be 0, body forces to be 0, and we solve the following problem. So because n is equal to 2, actually the vector valued variation in inequality can just be replaced by a standard scalar variation in inequality. And as I mentioned, we don't have an adjoint equation in this case. We get the following solutions, this bridge type structure. So we started off with initial data, this checkerboard, but also we started off with, we did computations with random initial data, and we got the same minimizer, so it seems quite robust. Similar thing for the cantilever beam, apart from, so again we're in 2 space dimensions, but now we have n is equal to 3, so that'll be 2 types of material plus the void, and again beta is 0, so there's no adjoint equation, and we've got no body forces. So, and we see that we have the following cantilever beam structure with, so what the different types of material we have is, so green is the soft material, so the elasticity tensor associated with the green, I think, is half that of the elasticity tensor associated with the hard material, which is the red material. And so we started off with random initial data, and this is the solution we found. Also works in 3 space dimensions, so the same thing, but here we've just got we just have 1 type of material plus void, so we get this quite robust. In this particular computation, probably the specified amount of material at the beginning was a bit large, which is why we have this, as I say, quite a robust cantilever beam. Probably we should have taken the amount of material to be less than to get a slightly more refined structure, but it would have this similar overall structure. And then finally, so here we're taking alpha equal to 0, and we've got this, we want to try and minimize the L2 error between our displacement and the objective displacement that we're looking for. And as I say, which is, we want U to be 0. We want the displacement to be as small as possible in the whole of the domain. And in this case, we just set, so it's 2 space dimensions. Again, it's just single material. It's not multi-material. We're just dividing the domain up into material or void. But in this case, we do now have, because beta's non-zero, we do have to solve the full system with the state equation and the adjoint equation coupled to the variational inequality. And so here Yeah, and we started with the checkerboard initial data, and these are the displacements. Sorry, these are probably far too small, but they are. It shows that it's the displacement is in general suitably small, so close to the objective displacement that we're looking for. This is the deformed state. So that's it. Thank you.
Question?
So, you didn't say, is the reason for non-well-posedness of the original problems of homogenization, and wouldn't you expect these materials to homogenize?
So yes, I mean you wouldn't get a unique solution in general. There'd be many solutions. That's why the
Would you get any? I mean, or would you get a solution at all in which the separate materials were separate, or would it?
So the answer is the answer is I don't know what solution you would actually get, but I think that the trouble is, that its uniqueness is the issue. So it would be interesting
But you didn't penalise, for example, the perimeter of the boundaries of each region, which would it be?
It'd be interesting to see what it did come up with.
You did. Sorry, I misunderstood that. I thought you were penalising the.
Oh yeah, we have perimeters. I thought
The perimeter of the whole of each region, where each material is.
Yeah. So all boundaries are penalised.
I didn't see that.
That was the Ginsburg-Landau function, was the approximation of the perimeter.
So any interface is penalised.
And what was what's the regularity of the? I mean, to set up the problem, what regions are you allowed to consider?
You're allowed to consider any region. So I don't quite understand what.
But you've got to be able to define that boundary somehow if you're applying some boundary condition, right? So you can't be any. I don't know. You need some kind of regularity.
Probably C1, I would imagine, but yeah.
But then you wouldn't expect the minimum necessarily to be attained, I suppose, because is it not?
No, it could well be that we're in some local minimum. Did you have a question?
Just wondering about the energy that is calculated. The energy keeps going down as you, right?
Yes.
But then if you stop at any point, the structure keeps changing. And how do you decide?
It does reach a steady state. The energy just flattens off.
Completely.
Yeah. In the computation stuff that we see.
Any more questions? No questions, can we speak again? We'll have a break and start again at 4 o'clock.